So actually, the title of the talk I gave is Turbulence and Universality in Accretion Disk. And really, I think it sounds very general, but the simpler question I think that I'm trying to ask with this talk is how universal, how sure are we that alpha should be 0.1? And so to provide some motivation for discussion, to a large extent, actually, my talk is going to be a review and very informal. So you should feel free to interrupt me if I say something that doesn't make sense. I didn't prepare slides. I just have notes. So just to motivate why I think it's worth asking this question, a brief recollection of, I think, what has happened with MRI studies in the last 10, 15 years. People have been looking for a process to generate turbulence in accretion disk, anomalous transport. Then the MRI came along. There were box simulations. The efficiency of transport as measured by alpha that came out from this first simulation was about 10 to minus 2. People said, well, it's a factor of 10 off. That's looking good. Then a few years later, there were the first global simulation. I think Armitage and John Hawley have been the people doing some of this. And then in some of this, at least global simulation, alpha was coming out as typically 0.1. And that was it, problem solved. I exaggerate a little bit, but people were satisfied, and it made sense. It was pretty satisfying that you seem to have the process that you needed with the right efficiency of Hamilton transport. And in the last few years, I think we have seen actually complications with this MRI simulation, so I'll come to that in a moment. And so I think it's worth, because of this complication and things are not looking so clear anymore, I think it's worth reconsidering the whole, the whole starting point about why we've been focusing on this alpha equal 0.1. So that's the first thing I want to do is just to remind you what the argument for why alpha should be 0.1. And then you'll see I'll go through basically a series of rather weak arguments about the possibility that alpha may not be universal and that we may have to deal with that, and that will complicate things significantly. But we should keep that in mind, I guess, is the point I'm trying to make in this talk. So how did we get to this number, alpha of 0.1? This has to do with this, these systems actually that I've listed here. I'll come to this a little bit next in the talk. But we have this cataclysmic variable system where we have, again, I'm going to do one of these diagrams, one star mass white dwarf accreting from a companion filling its Roche lobe, and that's going to be typically a sunset, and there is a stream hitting the disk here. There's a hotspot, which is something that's, I'll come to. And so you feed the disk at a steady rate, and you have this accretion disk, and you see most of the light coming from that disk. And one of the things that happens in a subset of all these systems, known as cataclysmic variables, is that they are unsteady disks. So you feed the disk at a steady rate, but the disk itself actually has huge variation known as outbursts. And so the light curve in optical, I'm simplifying things to the max here. The light curve in optical as function of time would be something like this. This peak of high accretion rate, low accretion rate, high accretion rate, low accretion rate. And this lasts typically for days, and this lasts typically is, week to a few weeks. And let's see. So there's been a great, some work on trying to characterize this disk, and it's beautiful work with eclipse mapping, which some of you may know about, some may not know about. Let me just also mention that because I think that's important. And this all goes to work done by Keith Horn and a series of people involved with this. But the idea is that these are bright nearby systems. You get a lot of photons, so you can use the fact that in some of this you're eclipsing the disk, maybe even the white dwarf and this hotspot during part of the orbit. And because you get enough photons, you can take snapshots of what you get as function of time in the eclipse. So effectively, you map the emission pattern from the disk. And what's shown is that at least in one or two systems, maybe even more, you get this. The flux goes as r to the minus, the effective temperature goes as r to the minus 3/4. So that is what you expect from a steady alpha disk. So that's a confirmation that, and I should say in outburst, or in systems that stay high all the time, you get actually this. So one of the things is that you know you have a quasi, in this high state, you have a quasi-steady steady state disk. Another thing that has been done, which I think is very important, there is observational confirmation that this disk is spreading viscously, as you would expect. Because one of the things you can do is map the time at which you get this hotspot to be eclipse, and if the disk spreads throughout these days, and you have like time scales for the eclipse that you can use actually to do that, you see actually in outburst the disk spread like this, which is consistent with this high-low state and viscous spreading. So you have a viscous disk, quasi-steady state, and basically you can say what's the viscous time for the evolution of this disk in the high state, and you get alpha equal 0.1. And the key thing here to keep in mind is that we have an idea of the mass transfer rate, we have an idea of the size of the system, the time scales we can monitor, and we get a value of alpha from this. And it's still a model-dependent value, one of the things. Yeah.
But it's sensitive to the viscous time at the outer regions of the disk,
yes.
Not even where the hydrogen ionization instability is, or where is
Yeah, that's the key, is that the evolution is determined by the slowest time in the disk, which is the viscous time at the outer edge, So the way you do this is you say T viscous is R squared over nu, then you say nu is equal alpha CS squared over omega K, okay? You know the mass, you know the size, so this you know. You're trying to get alpha, you know the size that you know. Then CS squared is really TC, central temperature. You don't know central temperature. So one of the things you have to do is to do a vertical model for your disk. So that's one of the points I want to make. This is somewhat model dependent. And you say, I do a one-zone model where I say TF to the fourth is TC to the fourth divided by tau, the optical thickness of the disk. One-zone relative transfer model. And this is actually sigma times kappa, where this is the opacity, and then the amount of mass you get. And so it's model dependent, because what you see is the flux coming out, and you need TC to estimate things. But by and large, people have done this game, played this game for a few systems, and Joe Smack is one of the big players in this game, and consistently you get things where basically alpha is order for the 0.1. Okay. This is where this 0.1 value comes from.
I have one comment.
Yes.
After 0.1 is the output stage. But in the quiescence.
Yes, I'll come to quiescence in a moment. Yes. This is where the issue of non-university comes in, actually, first.
About spreading, you drew the arrow to the right.
Yes.
I'm confused. Why is it to the right? It's beyond the hotspot.
Yeah, you see the hotspot move out because the disk spreads. So if you do a time-dependent model of these disks, which is what SMAC has been doing for decades, you find that you shrink, because there's a tide, so you remove angular momentum here, you shrink in quiescence, and then suddenly you have a lot of angular momentum transport in the high state, so this spreads. It's basically the origin of this spreading,
Yeah. You can go all the way to the Roshlov, of course.
No, then, I mean, the tide is a strong function of radius, so you have actually limited. But the point I want to make is that you have seen this disk spread viscously, so which is what you expect, but that's. Okay, so then the bottom line is, what else do we know about alpha in other disks, or even, to go to Shin's point, alpha in disk in quiescence? I would claim we just don't know anything. By comparing, this might be off by a factor of 2, 3, maybe if you want a big error burst, but it seems like consistently, I've looked at this argument, it makes sense. Quiescence. So one of the issues that if you do a model of these systems, in quiescence, the disk is not steady. It's very unsteady. So you run in a difficulty of, in a sense, your assessment will be very much model dependent. You do have to some extent, you cannot just plug in a single number like this, actually, is what I'm saying. So you have to do this time-dependent model, try to reproduce these curves. And when you do that, what you find is that the weak time scale that you get in many of these systems lead you to believe that alpha should be 10 to the minus 2, 10 times longer. And it's basically ratios between days and weeks. But there are systems, and one famous system that Joe Smack has worked on a lot about, known as WZGD, where this recurrence time, this is not so different for WZGD, maybe it lasts a little bit longer, but the recurrence time, so this time in quiescence, is actually decades. And that leads you to model it with alpha equals 10 to the minus 5. So there are two options. Well, at least two options. Alpha is not universal, or the models are wrong. But either way, we are running in this issue of we don't know so much except for these CVs in outbursts, and we go to quiescence. There might be indication that alpha is not universal, or that the models are wrong, which means that actually we don't know what alpha is. And then if you ask the question, do we know about the efficiency of Hamilton transport, turbulent Hamilton transport in any other disk in any reasonable way? The answer is no. That's basically what I want to go through, basically what we know about the disks.
What about soft X-ray transients, which is also modeled by this?
So they tend to be rarer, more distant, more difficult to get photons. So in principle, you could do all of this, but it's much better than with CVs, basically. And then the alpha values, also, I mean, yeah, it's also all over the place, basically.
Yeah, in the outburst, the alpha is 0.1. It's consistent, right? But in the quiescent, like...
That's what I'm trying to say, yeah. 0.1 comes from this high state.
Yes, the same thing.
Many people have looked at this over decades. It's consistently, we have something there. It seems to be 0.1, and I would say even in a few systems it's 0.1, so it appears to be somewhat universal. But anything else is I think, up in the air. That's
so I really wish Christelle was here, and you're not overlapping, right, because you're leading.
Yes.
Because she keeps on hitting us over the head.
Yes.
When we do spectral fits of black hole X-ray binaries, that alpha's got to be high. It's got to be 0.1. It's got to be 0.1, because that's what you need to explain the
okay.
X-ray outburst.
Okay, so
in the upper space.
Yeah. So then there's a question of how similar disks are to each other, and this is where and I think she has somewhat of a point for the high state.
Okay.
What I was discussing is the low state. For the high state,
so the high
by analogy, or actually, this is basically what I want to discuss. But now, what kind of accretion disks do we know about?
Can I ask for clarification here? 0.1 was for the high state, and for the low state, 10 to the minus 2 between 10 to the minus 2 and 10 to the minus 5? Is that what you mean?
Well, I mean, many systems are 10 to the minus 2, 10 to the minus 3, and there is some extreme with 10 to the minus 5. It's
and then,
but
how much between high and low does H change?
H?
What is disk height?
Well, how would we know that? Observationally, you have to ask yourself.
From the model, because m dot is different.
Oh, it's cold. Okay, there's another issue that we think is just become neutral in the low state, which is very interesting from the point of view of universally. I mean, several processes. I want to get to that in a moment, but we don't know the scale. Well, they would be cooler, so H would go down. I don't have a number for you. I could find it.
Roughly, H is proportional to square root of temperature.
Yes.
There's a difference about 10.
Yeah, that's right. Factor of 3 maybe.
Yeah.
2, 3. Yeah.
So in other words. And so CS, of course, is also going down. Yeah. So are you saying, and the viscosity, of course, is a factor of these three different things: alpha, H, and C.
Well,
and
if you believe that is the way you should model it, this is all model dependent.
Yeah. Yeah. Okay. Now it's quadratic. That's
yeah. So people use this alpha viscosity, and within that alpha viscosity, you still need. I guess I didn't clarify. Within that alpha viscosity, you still need to bring it down by 1 to 4 to the magnitude. Yeah. I didn't explain that. Yeah. All right. So these are the 4 types of accretion disks that we know of in nature, and essentially what I've done here is to list them. These are alpha disk model, and just try to figure out what sort of properties these disks have. And they have a number of features. A lot of stuff is going on in these disks that is different from one class of system to the next. This is basically what I want to point out. So these are the wide dwarf binaries. These are the CVs I mentioned. So you have this wide dwarf, few solar masses. Well, if it's a neutron star, it's 1 or 1.4 solar mass. This is the radial extent of the disk, 10 to the 6 to 10 to 11 centimeters typically. And then the temperature scale I'm quoting here is the central temperature. So for my typical alpha disk model, and I tend to pick the high state of all these systems when I discuss them. So you go to a very high temperature, 2000 K in the outer region, which means you have a neutral disk. So you go from ideal MHD to neutral fluid, or weakly ionized, I guess is a way to say it. And so that's the meaning of this ionization instability here in the properties of the disk. You cross this ionization threshold. In the inner region of these disks, you actually have a variable and significant contribution to from radiation pressure. That's one of the things to keep in mind about if we want to talk about universality. Then you go to the CVs, you go from 10 to the 5, maybe a few times 10 to the 5 to 10 to the 3K. Again, you cross this ionization threshold, which is believed to be the reason why you get this outburst. Actually, it is believed, and I could comment on this more if you want, but basically, there is a global instability, well, a discovered instability associated with crossing this threshold. It has to do with opacities, in the same way stars oscillate, you know, this accretion disk oscillates from a sudden change in opacity where you cross this threshold. This is a random radii, so much more reduced. You're not so deep in, so you don't have radiation pressure do anything significantly in these disks. Then you have AGN disks, 10 to 7 solar mass, million Kelvin to 100K. So you cross again this ionization threshold in AGN disk if you do it from 3 Schwarzschild radii to 10 to 5 Schwarzschild radii, which is what I've done here, which is about a parsec. Okay. Some of the stuff that's going on is that you do have a lot of radiation pressure in this inner region of this disk if they are quite close to Eddington. They appear, well, actually, they are locally gravitationally unstable, and very strongly so, because they also cool efficiently. So one of the things that has been discussed in some of this paper, there's a lot of work in all of this, I'm just citing a few, is that they would collapse gravitationally, form stars. The star would feed back energy, etc. It's a complicated business. We don't know how to make this disk stable, basically. It's a huge complication. And one of the things that Jeremy Goodman has been doing is saying, I feed back energy in the disk, can I get a stable solution? Yes, I can, only if I get alpha to be orders of magnitude larger than unity. Otherwise, this disk would collapse, and I cannot actually get a stable AGN disk. So that's a huge issue here. And alpha much larger than unity is and one of the things that has been mentioned. So very efficient angular-to transport. Then you have protoplanetary disks. 1 solar mass from the radius of the sun to 200 AU, 1000K to 10K. You are fully neutral, essentially. Well, you're essentially fully neutral in these disks. They do not appear to be gravitationally unstable, and they are not cooling. But one of the things that people have mentioned is the possibility that you might get MRI, MHD active, turbulently active surface layers, and in the middle a dead zone that is just hydrodynamically perturbed by the active layers. So you might have a regime where you have this induced hydrodynamical turbulence, because you have these top layers that are MHD, MRI unstable, and then you have this fluctuation, and there is some residual accretion in this purely hydrodynamical layer. And then GRB disks, they are more complicated, and I don't want to spend too much time on them, but there's the issue of radiation pressure, degenerate matter, gravitational instabilities. It's all pretty messy. We know little about these disks. I don't think it's worth spending too much time on them, because actually we don't really have much concern about this disk. One other thing I want to point is that the only ones for which the viscous time scale you might want to constrain observationally, the only ones for which you can do this are these guys. Because this viscous time scale is too long, viscous time scale is too long, and here the viscous time scale is too short. Because in fact what controls what's going on is really the feeding rate. You change the rate that you feed on a time scale much longer than the viscous time, so it's controlled by the feeding, not the viscous. So bottom line, we know alpha is 0.1 only in outbursts for these systems. And we don't know anything else. I mean, that would be my sort of conservative claim about this.
Again, just to emphasize,
yes.
But we also know that alpha equals 0.1 in outbursts in the black hole systems, or not?
Well, okay, so this is where I want to go actually to conclude with this, is that now, what I've emphasized here is sort of the microphysical properties of this disk in a sense, And some of the issues that have been mentioned recently is that the microphysics of where you are in the disk might affect the property of the turbulence and therefore the transport. And this is basically what I want to conclude with this. And the point is that you could expect radiation pressure being significant to modify the nature of the turbulence. In fact, the simulation tend to show some of this. And then you wonder whether that would affect your value of alpha. And in fact, if that's true, you would have an alpha that might change with radius. It's not universal anymore. If radiation pressure does change the value of alpha, in these disks, you would have alpha varying with radius. So it might not be 0.1. but we don't know.
But is it 0.1 at the region where the hydrogen ionization instability is happening?
Yeah, that I would argue the condition, if you take the same temperature and density condition, I would argue, I would expect it to be the same, yes.
Okay.
Because there is a bias toward universality in that sense.
Oh, but that's a theoretical bias. But
That's a theoretical bias. How would we
Okay.
know?
Because you still have light curves, you still have recurrence.
Yeah,
bias,
I
you still
think.
have outbursts,
I
time
think
scales.
you could make a case that's somewhat similar, but it's much less secure. So I think it makes sense to say that, but I think it's much less secure than what has been done with these Waldorf systems.
Well, how do you think so? in the alpha space, it's not so much complicated because in this emission.
Well, okay.
So-
What I'm going to say that Joe Smack has written a paper a few years ago where the paper is entirely on what is alpha in outburst. It fits light curves well mapped light curve for the system, and it gets to conclude that alpha is 0.1. To do that, you have to include a prescription for the tidal torque as functional radius. You have to include the variative transfer in the disk, and
it's just a small issue.
well, no, I don't think it's not clear to me because these fronts propagate in these disks. They don't go all the way in the systems because they're more extended.
Yeah.
Then you have an entirely neutral disk there. What's going on? How is it accreting?
Oh no, in the decay phase. The alpha viscosity, alpha parameter can be estimated in the decay phase,
Yeah.
not in the rising.
Okay, I mean,
That's something different.
I think it's fair enough. You're saying you believe it's also 0.1.
Yes.
I would claim that the job has not been done as cleanly for the system as been done for the series, basically. But it's a matter of personal opinion.
Yeah.
It's
But
fine
you
with
would
me.
believe it's 0.1 anyway, theoretically.
Yeah, it's consistent with 0.1, I would say. So I don't think there's a big problem there. Yes.
Perhaps you should let Kirsten finish on that.
Okay. Yeah. So I had a little bit more, but I think I will conclude by just saying, put a few things here, which is so now I realize most people in this room don't care about all these disks I mentioned here, and you care probably mostly about these guys. Right. So if we focus on, there's a lot of stuff that are worth looking into about this, but you don't care about this because there are no oscillations, okay? But let's say,
There are oscillations in AGN disk now.
yeah. So AGN is very interesting in
Yeah.
that respect, actually, because you would want to understand AGN this guy. But so if you care, even if you care just about these guys, I think then there are at least 3 issues that you want to consider. And I'm gonna phrase it. Let me see how I'm gonna do this. We know from the CVs that alpha is a function of m dot. Well, I'm saying we don't know alpha in the low state, but the evidence points to alpha changing with m dot. All these disk bundles have been built with alpha fixed, then m dot provided, and this is the structure you get. Okay, and so there are at least 3 ways in which the microphysics of the disk matters for transport in principle. One is this business of magnetic Prandtl number that has been mentioned, and these disks have various profiles of magnetic Prandtl number. One is the issue of radiation pressure over gas pressure, which I already mentioned. That changes from one disk to the next. In fact, it changes with radius, it changes with accretion rate, if that affects alpha. So you see, actually, I'm running into a problem here in my estimate, because if alpha depends on m dot, I plug in an alpha and m dot, and I say, oh, actually, the conditions are such that your alpha shouldn't be what you put in. And you change alpha, but you change actually the local condition in the disk, and this is actually nonlinear relation. So you actually don't know that this alpha disk are satisfactory even in this qualitative sense. Because if there is a dependence on the microscopic conditions, you actually don't know. Well, you should build like alpha as function of radius and m dot disk, and nobody does that basically at this point. So one of the issues is magnetic Prandtl number. Let me just say that most disks in nature have magnetic Prandtl numbers much less than unity, but Balbus and Henry pointed out that these guys that you care about have, in these simple alpha disk models, they have magnetic Prandtl numbers larger than unity in the few 10 Schwarzschild radii here, and then magnetic Prandtl number less than unity. So that could change the nature of the turbulence. Another thing that's going on, that I mentioned, is the radiation pressure contribution. So that is also variable with m dot, varies with radius, and is different from these guys to these guys. There is much more radiation pressure here close to the black hole, at the Eddington rate, say, than in these guys. This is the standard result. And then the last thing I would say that might matter is the degree of magnetization, which is something that has recently been reconsidered. So there's various things. For the CVs, there's a paper by Meyer and Meyer-Meister saying in WG Sagité, this system that has very long recurrence time, the companion is a brown dwarf. It has a neutral surface, neutral photosphere. You give to the disk material that is neutral, while the regular CVs, you give to the disk material that is fully ionized. So you're able to carry over magnetic flux to the disk as an initial condition at the outer edge, not in WG Sagité. So it appears that the degree of magnetization, it's possible that the degree of magnetization of your gas that you start with could affect how the disk behaves, basically. 10 to minus 5 alpha instead of 10 to minus 2, for instance. Another thing that appeared recently is Yuri Levin and Andres Johansson have this strongly magnetized sharing box simulations, and they show a different behavior essentially of the turbulence from the regular simulation starting with weak magnetic field, and they get alpha of 0.1 in their local, instead of 10 to minus 2. So again, the degree of magnetization you start with might affect the efficiency of transport. So bottom line is that it looks like all of this could lead to non-universality of turbulence and the efficiency of hydrogen transport, and it's worth keeping in mind, basically. That's my point.
5 minutes for questions and discussion.
The old models by you mentioned my Hofmeister, they calculated these S curves, and I thought the two different branches always actually corresponded to two different alphas. Isn't that right?
Yes.
So.
And this business of fitting these curves,
right.
Base versus weaks, in these time-dependent models,
So the only problem with these models is that they are in principle realistic stratification models, have radiation and ionization and everything in it. The only shortcoming of this is that the alpha has to be put in. So would you think it's a significant progress if one can produce shearing sheet simulations with exactly these two different conditions?
Yeah. So
the trouble with shearing sheet, of course, is that sigma, or maybe also the advantage is, the trouble is that sigma is the conserved quantity then.
Well, no, wait,
so
okay.
In the S diagram,
what you're proposing is interesting, but before you go there, you have an issue. Charles Gamey and I pointed out that these low states are very weakly ionized.
Mm-hmm.
And, if you do, the point is that if you do a shearing box simulation with this degree of weak ionization, you kill the MRI.
Mm-hmm.
And that needs to be reconsidered, I think, because, Steve Albus doesn't think that's what's going on. So I think there is a number of issues there. But the point is that it's not clear that you have a way of generating turbulence for this, that we know of how doing it. Yeah. If you could do a full cycle in a box, it would be very interesting. But you have an issue of how do you deal with this very low degree of ionization.
You would never be able to do a full cycle, I think, because you would need to change sigma.
What is sigma?
The integrated disk height, which is mass, essentially.
Oh, you mean
it's the mass of the shearing box.
Okay, yes. You have practical issues, yeah. So you would have to do it global, yeah. Well, one of the things Jim Stone has done is he has, let me see, what did he do? He has a paper where he starts with a shearing box, resistivity essentially 0, so you get the MRI going on, and suddenly it turns up the resistivity, because that's what's going on when you go in this low state. You must go through a phase where resistivity actually increases dramatically as you become more and more neutral. And what he finds is that you indeed kill the MRI in this specific simulation, but you have residual turbulence for hundreds of orbits. And that might be enough to lead you to this alpha, actually. But yeah, I mean, that's all I'm going to say. I think there is more work to be done in that direction because it's interesting, yeah.
And then how?
I guess I don't know if it's really turbulence or waves.
And how do you envisage the disk recovers from this low state then?
That is completely unknown. I've worked in this area for several years. I think nobody has a good way of doing this. But I think it's just you have to have a trigger for the ionization. Is my own favorite scenario. But we don't know what's going on in quiescence.
But I mean, you have an m dot still imposing more and more mass onto this non-turbulent thing. So the stuff cannot accrete, but it's having a stronger and stronger load.
So you build a torus.
Yes.
And then the question is, at the center of the torus, can you suddenly become ionized? This is a good thing to consider. Yeah, it's not been done.
So you are saying basically something which. I think we kind of know for many years that disks in CVs are being understood and other disks are not so well. But this difference between being understood and not so well is not connected to what we do in this room. It is not because theory of these disks is better. It is that we have better connection between theory and observations. So if we have some kind of a practical moral to take from what you said, would you agree that it is not that we must be theoreticians, smarter and build models, but that we should have this kind of solid information from the observations of the
I think that's very important. I mean, one of the reasons I'm making this point, and also the discussion I tried to generate yesterday, is that, again, I'm running this turbulent simulation of atmospheres. And the business there is not about knowing what creates a turbulence. The business is to simulate the turbulence well. Because, you know, if you want to predict the weather, you have to have the right vortices and they propagate and advect. So then you have all this detailed information about the turbulence. Here, we have only a global constraint on the turbulence, the efficiency of transport, only in a subclass of systems, and we have almost nothing else. Actually, if some people can somehow come up with a way of constraining things optionally better, I think that's very important, yes. So I agree with that.
So you're advocating that we change fields?
Let's change rooms.